welcome to the channel. This is the PLC Tech, and today's video is a remix of troubleshooting cable problems by using a multimeter to measure the conductors and using a resistor to give you a known resistance value across the two conductors. By doing this, it gives you a known value to measure and be able to detect water grounds and continuity. By the way, I just wanted to make you aware this video was recorded a few years back, and I'll put a link to the original in the comments or the description, sorry. And the voice in this one is text to voice with AI, because man, when I recorded that thing years ago, it was a mess. If you want to get a laugh, go back and watch that video. Anyway, I digress. On to the video.
Warning before you start troubleshooting cable problems. You need to disconnect and isolate conductors and cable to be tested from power and communications. Then put a known termination resistor value at one end. Now I will show you that. In this situation, we just use a wire nuts and a 120 ohm resistor between a pair of conductors. This is typical for a terminating resistor on Modbus RTU system cables. Usually they're mounted inside the box or made into the circuit board. I'll show you that in a minute. Let's imagine that this 120 ohm resistor is on a communications. If we read with an ohm meter on the other end of this cable, through the resistor and back again, we will read the 120 ohm resistor plus the resistance of these two conductors for whatever length they are. This is just one example of a circuit board with a termination resistor installed. Now you can see both ends of the cable, the terminating resistor, and the other end, the cable's jacket strip back. So we can separate the conductors so that we can meter them. The meter is currently reading in resistance, in ohms. If I touch the two leads together, we should get a shortage condition and reading near 0 ohms. If we measure just a resistor right here across it, we should read the roughly 120. Actually, it is 118 ohms. Now, if we go the opposite end of this cable, measure that pair of conductors with the resistor between them, we can see it basically reads the same as that resistor. That is because this is a very short run of cable, and the conductor resistance has little to no effect on the baseline 118 ohm resistor reading. I'm going to show a chart that gives you the resistance you would have to add per 1,000 foot based on the conductor gauge and number of strands in that conductor. Now, we know that we're reading good from one end of the conductor through the resistor and to the other end of the other conductor. This scenario is 118 ohms. Remember that for future reference. That said, we're making good continuity through that particular set of conductors. So, do we have issues between other conductors? Let's find out. So if we leave ourselves connected to one of those conductors and go to the shield wire, for example, what do we read? Well, we're reading in the megaohms. So noise, moisture, something, but it's in the megaohms, so it's not a concern. Here between the other conductors, we are open and megaohms on it as well. That all looks good. That's what you want to see. Since we know there's nothing connected to the other conductors, we can check between them to make sure we don't have any shorts. There shouldn't be. We can measure resistance across those as well. It should also read an open circuit. Okay. So we're going to say everything is good in this situation. Next, we're going to simulate some conditions that are typical problems you may see. What we've set up here is nothing more than a bucket of water. It's not quite a real-world scenario, but you will see how it can be affected the resistance. For example, if you have a splice in a cable, let's say underground or a collapsed conduit or whatever situations that may be the cause, where a splice in the cable is being damaged, and that splice gets moisture in it or has corrosion. That's what we're going to simulate here. The cable we've got is spliced together is not wrapped in tape or sealed. It'd be kind of hard to simulate if it was wrapped, But the principle is still the same as far as seeing that water ground or even corrosion will do to the resistance at this point, creating an increase in resistance across the conductors. You'll see what I mean in this simulation. So here's our two ends again. Here's our resistor. We're going to do basically like we did before. Measure resistance on the two conductors that have the 118 ohm resistor on them without touching anything else. All right, 118. And then we're going to take our splice, submerging in water to simulating that splice has gotten water in it or has corrosion. You'll notice the resistance changed slightly, went down some. So you would think, okay, that is not right. It dropped because of the water grounding between the conductors. This vary on your cable length and your cable resistance because of the size of cable, but still has the same effect. Let's look at it a different way where the difference is much more noticeable. Let's measure over to our shield wires and other conductors. Now we're in the kiloohms. We're also bouncing around quite a bit. Now these numbers are not going to be exact in every situation. Now you can see where we are no longer reading megaohms. We're reading kiloohms. And you'll see that result will depend on which splice or connector is getting more or less moisture into it. In that scenario, we're measuring water ground or corrosion between all conductors. Obviously, we have submerged the whole thing in water. Now be mindful that the conductors that have the resistor actually went down, but not enough to where it would worry you. But it is affected by the water ground and will have problems if used for communications. However, the other conductors are obvious between them because they are not measuring fully open circuits like before. So they are all really bad and will pull your signal down to where it would be affected with intermittent comms and cause communications problems. All right, now let's look at a damaged cable. They will measure as open or shorted as it is measured between the two conductors that should measure as open, that is the damaged side. Now we look at the other side. It looks pretty good and may not be obvious that it is damaged. So keep that in mind. We're going to take a measurement from the shield to this conductor to measure and see if it is open as the cable gets flexed. You'll notice that it'll go from an open circuit, as it should be, to a short circuit and is bad. These can be very hard to find if they're intermittent. You can see it doesn't take much for that cable to clear up, but we wanted to show you that. You can see that the cable doesn't have to look very damaged to be damaged inside.
Please like, comment, and share this video to help others. Also, let us know what you would like to see next in the comments.